Hello and welcome to episode 4 in the series Calculus 101. And today, ladies and gentlemen, I introduce you to the derivative. We finally begin our journey into calculus. Today we start our first branch of calculus, differential calculus. So without any further ado, let's get started. A derivative is a fancy way of saying instantaneous slope. So if, let's say, we have a graph over here, f of x equals 2x plus 1, what will be the derivative of this graph? Well, as I just mentioned, a derivative is just a fancy way of saying slope. So the slope of this graph, as we all know, is 2. Yes! We're done! We're done with derivatives. Well, not quite yet. Let's just do a small recap. So the slope of this graph will be represented as the change in y over the change in x. Or another way of writing it could be y2 minus y1 divided by x2 minus x1, where x1 comma y1 is this point right over there, and x2 comma y2 is this point right over there. So y2 minus y1 will represent this distance, and x2 minus x1 will represent this distance. So delta y divided by delta x will give us the slope of the graph. However, this is only true if we have a straight line. What happens when we have, let's say, a quadratic expression? In that case, we have a problem. Because as you can see, the slope of the graph keeps changing. So what is the slope of this graph? The first question is that even a valid question? And the answer is no. That question shouldn't even be asked. If you ask someone what is the slope of y equals x squared, that is not a correct question, since it does not have a defined slope. The correct question would be, what is the slope of y equals x squared at x equals some certain point? So let's say we wish to find the slope at x equals 1. The first thing we must do is draw a tangent line to the graph. A tangent line is a line that touches the graph at only one point. Our goal right now is to find the slope of this tangent line. So let's go by it. Once again, slope equals change in y over change in x, and whoops, Houston, we have a problem. Because as you can see, we only have one point that is defined. And to find the slope of any line, we need 2 points. So what do? So what we do now is we take another arbitrary point. Let's take 2, 4, just the random point, and draw a line straight through there. Whoops, we have another problem. This orange line looks absolutely nothing like the black line. Remember, our goal is to find the slope of the black line. So we have to get or morph the orange line as well as we can to look like the black line. So what do? So let's call this distance over here h. First thing we must do is to find the slope of the orange line only with variables, no numbers. So this point over there, let's call it x comma f of x, and this point over there, let's call it x plus h comma f of x plus h. So generally when we're trying to solve for slope, we will do y2 minus y1 divided by x2 minus x1, which results in f of x plus h minus f of x, which is y2 minus y1, divided by x2, which is x plus h, minus x1, which is x. So we can simplify this. So whatever h is, we can finally find the slope of the orange line. Now remember, our goal is to find the slope of the black line, so don't forget that. So how do we once again morph the orange line to look like the black line? What we can do is take h to equal 0. If we take h to equal 0, we have a problem. Because now we're going to be having f of x minus f of x divided by 0. Forget about the numerator equaling 0. Nothing can be divided by 0 because it's undefined. So does that mean the slope of the graph at that point is undefined? No. So then what do? So this, ladies and gentlemen, is where we use our knowledge of limits. Because if you remember, if there is a point that is undefined, you can simply take the limit as x is approaching that point. So how do we find the slope of the black line using limits? So what we can do is the slope of that black line equals the limit as h approaches 0. Because once again, we have to get the orange line to look like the black line. So if we're getting smaller and smaller values of h, as you can very well see, it is looking more and more like the black line. So the limit as h approaches 0 of that function over there, which is f of x plus h minus f of x over h. And this, ladies and gentlemen, is what we call the derivative. Another way of writing this instead of m would be f prime of x, which basically means the derivative of f of x. Hopefully that made sense. So this right over here definitely deserves a standing ovation. We have successfully formally defined the derivative, because what this means is if we take any graph and we're finding the limit as this h value is approaching 0, we can find the slope at any point. So as I mentioned in the beginning, we want to find the slope when x equals 1. So let's solve it. So what we can do is solve for f prime of 1. So f prime of 1 is going to be equaling the limit as h approaches 0 of f of x plus h. So what is f of x plus h? So x right now is 1, so 1 plus h squared, since the graph is x squared, minus f of x, which is simply 1 squared, which is 1, divided by h. If we simply expand this, we can get the limit as h approaches 0 of 1 plus 2h plus h squared minus 1 divided by h, which now equals the limit as h approaches 0 of h squared plus 2h divided by h. Just going to draw a line there. We can factor out the h and we can finally say the limit as h approaches 0 of h plus 2 divided by h. Cancel the h's out and we get the limit as h approaches 0 of 2 plus h. When h equals 0, we get the slope, or the f prime of 1, the derivative of y equals x squared at x equals 1 equals 2. We can even find a general expression for the derivative of a graph. Instead of taking x equals 1, we just generally go by and expand it. So we will get x plus h squared, which is x squared plus 2xh plus h squared minus x squared divided by h. So now these will cancel out and we can get 2xh plus h squared divided by h, which then once again we can factor out h to get, cancel the h's, and ladies and gentlemen, we have found the derivative of the graph f of x equals x squared to be, when h is 0, 2x. That means when x equals 1, all you have to do is plug it into the derivative and we get the slope of the graph. So what happens when x equals 2? Plug it into the derivative and we see the slope is equal to 4. Voila! Ladies and gentlemen, we've successfully defined the derivative. So obviously you could do this for any graph. It doesn't necessarily have to be for f of x equals x squared. It does include any graph whatsoever. All you have to do is plug the values in, evaluate them, and you get the derivative. Now obviously this isn't the most efficient way, and that is why in the next episode I'm going to be covering derivative rules, such that we can evaluate the derivative of f of x equals x squared in one step. However, before I sign off, I do want to cover one thing, a differential. So instead of seeing this notation over here, many times you also may see this notation, dy over dx. So if you remember originally when I spoke about slope equaling delta y over delta x, that's the exact same thing. But instead of delta y over delta x, it's simply dy over dx, where d does not represent delta anymore, but it represents a differential. So what really is a differential? A differential can be thought of as an extremely small change in. Once again, over here we can see h is approaching 0, and therefore we are taking extremely small changes in y divided by extremely small changes in x. Because remember, h is approaching 0. And that is basically what it means. So delta y can really be anything. It can be 100 minus 5 if you want. But dy is an extremely small change, or once again, a differential. You can also write this as df of x over dx, which once again is the same thing, which basically is a small change in f of x divided by a small change in x. Once again, they do look very similar. The only difference is instead of the delta symbol, we are using d. Now remember, these are treated as numbers like 0.05 or 0.3 because once again, they are simply values where they represent a very small change. Thank you so much for watching. I really do hope you enjoyed that, maybe understood a little bit about derivatives. Once again, differential calculus, we finally started strong because this is the first branch of calculus, and believe me, it's going to be fun. Thank you so much for watching, and until next time, stay sharp.